In section 2.5, we're going to be graphing what we call piecewise functions, or in your textbook, they'll call these piecewise defined functions. And I'm lazy, so I'll just say piecewise function. And it's exactly what it sounds like. These are functions that are defined in pieces. We saw that in the last section when we looked at the absolute value function. Notice that the absolute value function is defined in two pieces. It's equal to x if x is greater than or equal to 0, and then negative x if x is less than 0. So something to remember is that f of x, our function, remember that's just a y value. So what we're saying is that if you put in x values greater than or equal to 0, then you get back a y value equal to x. So each one of these pieces is an equation, y equal to whatever it is. So on the negative x, that's actually y equal to negative x. So it says that if you put in an x value that's less than 0, then you get back a y value that's equal to negative x. Something else to remember is that these inequalities are actually intervals. If we look at x greater than or equal to 0, that would be 0 with a bracket. We include it because it's greater than or equal to. And then it would be all the x's larger than, so that would be to infinity. And when x is less than 0, that would be the interval from negative infinity to 0. So let's go ahead and graph the absolute value function. Now we all know what it looks like. We saw it in section 2.1, and then we transformed the absolute value in 2.2 and 2.3. So it's not going to be a surprise what the graph looks like, but I would like to take a familiar graph and show you how you actually graph your piecewise functions. Again, it's going to be in pieces. So what we're going to do is we're going to look at the top portion, which is y equal to x. And we're going to plot some points. We have to be clear about what x value we're starting with, and that comes from the interval. Notice that our interval starts at 0, and it actually includes 0. It's got that bracket there. So when I graph the point 0 for x and 0 for y, if I put it in y equal to x, it's going to be a solid dot. So this is going to pass through the point 0, 0. And then I can just get a few more points that are greater than 0 because that's what the interval says. So maybe 1, 2, and we'll see what it looks like. If I put in 1 for x, I get 1 for y, 2 for x, 2 for y. So it's going to pass through 1, 1, 2, 2, and I could put more points in, but I can already see that I get this portion of my absolute value graph, and this is when y is equal to x, and it's just on this interval starting with 0 to infinity for those x values. Let's go ahead and look at the second part of this graph, which is y equal to negative x. Again, I'm just going to make a table of values. The starting x value that I'm going to plug in is the one that I see in the inequality. So this says x is less than 0. So I'm going to start with 0 and then enter in x values that are less than 0, maybe negative 1 and negative 2. Because I'm only graphing y equal to negative x on that interval. If I put in 0 for x, I get 0 for y. But notice it's strictly x less than 0. So technically, this would be an open circle. But in the prior piece of my graph, it was solid. Well, maybe I'll just do this in red so we could see the difference. All right, so if I put in negative 1 for x, then I get negative negative 1, which would be a positive 1. I put in negative 2 for x, it's negative negative 2, which would be a positive 2. So it's going to pass through the point negative 1, 1, negative 2, 2, and I could keep going, but I can see that my graph will do exactly what I expected it to do. So this is our absolute value graph. On the left-hand side, it's y equal to negative x, but just for x values from negative infinity to 0. And then on the right-hand side, the graph is y equal to x from 0 to positive infinity. And that's how you graph your piecewise function. You look at each piece separately, plot some points, and draw your graph. You just have to be aware of which x values you're putting in. So you have to be very conscious of what those inequalities are. The rest of example 1 says, is the function continuous on its domain? Well, what is its domain? I see that the domain from the graph is going to be negative infinity to positive infinity. Now, I actually didn't have to look at the graph. I could have gone back up to my intervals. Let's look at these intervals here. Notice that at the bottom, I'm starting with negative infinity, and I get all the x values to 0. But it's a parenthesis, so that doesn't include the x value of 0. But then my second interval, the one above, does include 0. So now I've got all the x values from negative infinity to 0 all the way to positive infinity. So if I just look at those inequalities as intervals, I can see that my domain goes from negative infinity to positive infinity. But the question is this function continuous on its domain? And yes, it is, because remember, continuous just means that you can draw the graph without lifting up your pen, which I can do. And that just means there's no holes or no breaks in your graph. What I would write is that it is continuous, or I'm just going to put continuous. Let's graph another piecewise function. In example 2, we have f of x is equal to 3 minus x if x is less than 3, and 2x minus 4 if x is greater than or equal to 3. What's really nice about this textbook is when they look at their piecewise functions, they'll typically start with the smallest interval or the smaller numbers and then go to the larger ones. So it's easier for you to graph from left to right. This first inequality, x less than 3, that would correspond to the interval from negative infinity to 3. And then we don't include 3 because it's strictly less than, so it'd be a parenthesis. X greater than or equal to 3 would be starting at 3, and we go to positive infinity. So we have two pieces to our graph. One piece of the graph will be from negative infinity to 3. The other piece will be from 3 to positive infinity. So let's go ahead and write our equations. The first is y equal to 3 minus x. Now I could see that this is a line, but even if you didn't know it was a line, you would just plot some points. Remember, you can always refer to a graphing device such as a calculator or go online to Desmos to double check your graphs. I'm starting at 3 because that's the number that is in my inequality. So that's what I'm going to put in for my x values. Sorry, my pen got a little weird. I'm going to start with the 3 that is there, and then I'm going to put in x values smaller than 3. So if I put in 3 for x, I get 0 for y. Now remember, this is strictly less than 3, so if I were to graph this point 3, 0, it would be an open circle. But it doesn't matter. That's still my starting point, whether it's open or solid. And then I'm going to look at x values smaller than 3, so maybe 2, 1. And I personally know this is going to be a line, so it's going to be just a few points is all I'm going to need. 3 minus 2 is 1. 3 minus 1 is 2. So it's going to pass through 2, 1, and that would be solid. And then 1, 2, that would be solid. And that's enough points for me to draw my line, but feel free if you want to do more, maybe put in 0 for x, and you'll get 3 back for y. This is enough though. And you draw your graph. So this portion of the graph, and this is typically what we do when we graph our piecewise functions, is we will label each piece. This would be y equal to 3 minus x. And I'll go ahead and use a different color again so we can see the two different pieces. The next piece would be y equal to 2x minus 4. And I know that that's going to be a line. But again, even if you didn't, you would just plot points and see what the graph looks like. I'm starting at 3 because that's what my interval tells me to do. If I put in 3 for x, I get 6 minus 4, so I'll get 2 for y. And that's going to be solid because I include 3. So 3 comma 2 would be a solid. And then I'm looking at x values larger than 3. So I could put in 4 and 5 and see what the graph looks like. If I put in 4, I have 8 minus 4, which is 4. We're going to pass through the point 4 comma 4. And then 5 would give me 10 minus 4, or 6. All 3 points line up, and I knew it was going to be a line anyway. So I just draw my graph and label this y equal to 2x minus 4. So that's it. Graph it in pieces. Just be aware of what your x values are. So is this continuous on its domain? Well, first of all, what is its domain? Again, you can go ahead and look at the intervals. So I would be looking at these intervals here, or you could look at the graph. If I look at the intervals, my interval starts at negative infinity, and then I get all the x values to 3, but it doesn't include 3 because of the parenthesis. However, when I look at the second interval, it does include 3. So far I've got all my x values from negative infinity to 3 all the way up to positive infinity. So I have all the x values from negative infinity to positive infinity. That would be my domain. Again, you could have just looked at the graph as well. Is this function continuous on its domain? No, it's not continuous. And in fact, I can tell you where it's not continuous. It would be at x equal to 3. If we were to sketch the graph, we have to lift up our pen once we get to x equal to 3 so that we can continue on with the second part of the graph. So we do have a break when x is equal to 3. Oftentimes, instead of saying not continuous, we will, I don't want that. We will say discontinuous. So I could have written discontinuous at x is equal to 3. Let's just graph a few more of these piecewise functions. And then the last problem will be, if we're given a function, can we figure out what the piecewise function is? In part B, notice that this piecewise function has 3 pieces. And you can have as many pieces to a piecewise function, as you want. You could have 4, 5, 6, and so on. So this just happens to be in 3 pieces. Maybe I'll go ahead and look at each piece at the top, maybe write it off to the side. So this says f of x is equal to 3. So that says y is equal to 3 if x is less than or equal to negative 3, which would be the interval from negative infinity to negative 3 with a bracket because we're including the negative 3. The next piece is negative x, so y is equal to negative x. The interval here is x is greater than negative 3 and less than 0, but not including, so parentheses negative 3 to 0. And the last is x squared, so y equal to x squared. That would be x is greater than or equal to 0. Now, as we go through these graphs, you might have to go back to 2.1 where we looked at our basic graphs, because notice the last one, y equal to x squared, that would be our squaring function. So you might have to review stuff like that. Let's go ahead and graph y is equal to 3. Now I know it's going to be a horizontal line. It's going to start at x equal to -3, y equal to 3, and then just go towards the left forever. If you are not sure, then you would just make yourself a table of values. Remembering that we're starting with whatever our interval says. So it says we're going to look at x is equal to -3, and then you can put in x values smaller than -3. So when x is -3, y is 3. -4, y is 3. -5, y is 3, and so on. And now since we're including the -3, at -3, +3, it's going to be solid. -4, 3, again, you didn't have to do all these points. If you realize this is just a horizontal line, you would have your starting point and you could just draw your horizontal line. I'll go ahead and label this y equal to 3. Next, we have y equal to -x. So I know that's going to be a line. I'm going to plug in some points. I'm going to start with -3 because that's what my inequality or my interval tells me to start with. And I'll end with 0. I have to do open circles because it's strictly x greater than -3 and x less than 0. So again, going to be open circles, but I can still put these points in. If I put in -3, y is going to be equal to a -3 or +3. If I put in 0 for x, I get 0 for y. It's going to pass through the point -3, +3, and this should be open. But really, with this graph, it doesn't matter because we've already got a solid dot there. So we already have a point graphed at that point. But I'm doing the open circle to remind you that with this second piece, that point really doesn't exist. And then at the point 0, 0, it's going to be an open circle as well. So maybe I want to pick some other points, choosing x values between -3 and 0. Maybe I'll look at -1. If I put in -1 for x, I get a +1 for y. And I could try -2 and I'll get a +2. I'm doing this just to double check to make sure that my math was correct. And there is my second piece of my graph. This would be y equal to -x. The final piece is y equal to x squared. Again, if you don't remember what that graph looks like, you can go back to the 2.1 and refer to the squaring function, or you can use a graphing calculator or a graphing device. You can use Desmos, the online calculator. I actually really like Desmos. However, I am very familiar with this graph, and I know because it has the x squared, it's going to have a curve to it. So far, we've been graphing lines. Yeah, but now we're going to get something that does a little bit of curving. So I'm going to do the same thing I did before. I'm just going to put points in. Now my interval says that x is greater than or equal to 0. So 0 would be my starting value. If I put 0 in for x and square it, I get 0 for y. And this is going to be solid. And now let's try some more. Maybe 1 for x, square it, I get 1 for y. 2 for x, square it, I get 4. Now if I put in 3, I'm off this graph, but I already know that this is that scoring function, or if you're familiar from algebra, that would be called a parabola when we graph it, and it's going to have a little curve to it. Now this is our y equal to x squared, and I have graphed my function. So let's go ahead and answer the question about continuous on its domain. I'm going to go ahead and go back up to the top and look at its domain. Now I could look at the graph and see that the domain is negative to positive infinity, but I can also look at these intervals and ask myself, do I get all the x values? And I do. I'm starting with negative infinity, going all the way to -3 inclusive. And then the next piece is starting at -3, and it doesn't matter that it's not included because it was included in the prior interval. So far we're going from -infinity, -3, continuing on through 0. Don't include 0, but I do include 0 in the next interval. And then that goes to +infinity. So I have all my x values listed there from -infinity to +infinity, and that would be my domain. So is it continuous? And the answer is yes, it is continuous. If I were to sketch this graph, I don't have to lift up my pen. I can sketch the whole graph without stopping. There are no breaks. So yes, continuous. Okay, one more piecewise function. This one has 3 pieces as well, and this one's a little bit more complicated. Let's see, our f of x is equal to x plus 1. So remember that would be y equal to x plus 1. If x is greater than -5 and less than -1. So notice there's no -infinity, +infinity in these inequalities. This interval would be -5 with parenthesis, comma, -1. The second piece is y equal to x squared. So I see that scoring function, but it looks a little bit different than what I'm used to because I have a -2x minus 3. But regardless, we'll just plot points and see what it looks like. I see that because I have that x squared, it will be that curvy graph. And I'm going from -1, but it's a bracket because it's x greater than or equal to -1. And then I'm going to 1 with a bracket because x is less than or equal to 1. The last piece is y equal to the square root of x. So remember that would be our square root function. And we've transformed this many times in 2.2 and 2.3. The interval would be 1, comma, 4, including 4, so it would be a bracket. So these are the 3 intervals that I'm going to graph my 3 pieces. We'll start off with the y equal to x plus 1, makes our table of values, starting with -5. Now remember the -5 has a parenthesis, so we're not including, that point actually doesn't exist on the graph, but we're still going to use it as a starting point and do the open circle. If I put in -5 and I add 1 to that, I get -4. And then we're ending off this interval at -1. If I put in -1, I get 0. So -5, -4, again, that would be a parenthesis, so it would indicate an open circle. And then at -1, 0, that's an open circle as well. So I could connect these pieces, but let me put in some more values, x values between -5 and -1, just to double check my math. So what if I had something like -3? And I add 1 to that, I'll get a -2. So -3, -2 does exist, and it looks like these points all line up. So I'll go ahead and draw my line. This is y equal to x plus 1. Our next piece, this one's going to be a little bit more complicated, but I know because I have the x squared, it is the squaring function. So I know it's going to curve. I just need to find some points. So we're starting with -1 because that's what my interval tells me to start with. If I put in -1 for x, I'm going to square it. So I'm going to get +1 minus a -2, so +2, minus 3. It's going to give me 0. I'm going to go ahead and graph that. Now the -1 was solid. So -1, 0. Oh, so now we no longer have a hole there. That's solid. If I put in the ending value of positive 1, I get 1 minus 2 minus 3, which would give me a negative 4. So positive 1, negative 4, and that would be solid. And I know it's going to curve, but maybe I want to get maybe at least one more point so I can kind of see how it curves. The only x value that is nice between negative 1 and 1 would be 0. If I put in 0, I get a negative 3 back. So 0, negative 3, and then I can just go ahead and connect the dots. And it does curve. So again, if I were to graph this, it would be y equal to x squared minus 2x minus 3. And then we'll do our last piece, which is familiar to us, the square root of x. We are starting with an x value of 1, although it is a parenthesis, so that's going to be an open circle. If I put in 1 for x, square root of 1 is just 1. And then at the point 1 comma 1, I'm going to draw my open circle. Notice that this ends at 4. I'm going to put that ending value of 4 in. Square root of 4 is 2. This will be 4, 2, and it's going to be solid. And I could put in 2 and 3 to double check my graph, but I think I'm going to have to use a calculator because I don't know what the square root of 2 is without a calculator. So you can do some more points and just do a decimal approximation with your calculator. But I already know what the square root, function looks like. It kind of curves this way. And label it as y equal to the square root of x. Now, is this continuous on its domain? Well, what is the domain? In our prior examples, the domain just went from negative to positive infinity. But when we look back at our intervals, we're starting at negative 5, and it's a parenthesis. We're going through to negative 1. We don't include it because it's a parenthesis, but then on the second interval, we do include the negative 1, so that's included. Then we go to 1, inclusive. We start at 1, and then we go to 4, and we're including 4. And then I'm done. The domain is negative 5 to positive 4, and we don't include the negative 5, so parentheses, but we include the 4, so that would be a bracket. Now, is this function continuous? And the answer is no, it's not. It is discontinuous at x equal to 1. Because if I were to sketch this, I would have to lift up my pen once I hit the x value of 1 to finish off sketching the graph. This last example is a little bit challenging because we have a graph, but now need to figure out what our piecewise function is. So the first thing I like to do is first figure out what my intervals are. If we look at the left-hand side and we look at this graph that I'm going to sketch in blue, the x values go from negative infinity to 1, and it includes 1. So I can see that that would be parentheses negative infinity to 1, and I include 1. So I'm going to translate that to my inequality. That would be all x's that are less than or equal to 1. And now this horizontal piece, that goes from x equals 1 to x equal to 2. It's an open circle. So it's going to be parenthesis 1 to 2 with a bracket. It includes 2. That would correspond to the inequality 1 less than x less than or equal to 2. And then my last piece, open circle, but the line goes up to positive infinity. That gives me x values from 2 with a parenthesis because it's not included to positive infinity. That corresponds to x greater than 2. So now I have my intervals and my inequalities. I'm going to figure out what these graphs represent. If we look at the blue graph, that looks like the graph of y equal to x squared, the squaring function. Imagine if we were to continue this on, it looks like y equal to x squared. So that's what I am going to write, and then I am going to double check by plotting some points. So let's suppose this is y equal to x squared. Well, if we look on this graph, and we'll look at the nice values, we have that the graph passes through negative 2, 4. Let's look at another nice one. Negative 1, 1, 0, 0, and 1, 1. So does y equal to x squared correspond to those points? If I put in negative 2 for x, I get back 4, so yes. If I put in negative 1 for x, I get back 1 for y. 0 gives me 0, and then if I put in 1 for x, I get 1 for y. So it appears that this is y equal to x squared. It has the same shape as the squaring function, and it passes through all those nice points. The next one is a horizontal line, so I know it's going to be y equal to some number. And since I see that that graph corresponds to a y value of 3, I know that this is y equal to 3. Let's say I didn't know. Well, then I would just simply make a table of values and see if the points pass through the points on the graph. So even though we have an open circle when x is equal to 1, we can still put that in. If x is equal to 1, y is 3. If x is equal to 2, y is 3. And in fact, if I put in any value between 1 and 2 for x, I get y is equal to 3 on this graph. So it appears that that piece of the graph corresponds to the equation y equal to 3. The last piece, open circle when x is equal to 2, and then we have this line that goes on to infinity. So I know it's a line. Typically, lines can be written as y equal to mx plus b. So I need my m, I need my b. To find the m, all I have to do is simply count. Find 2 points, and I could use the open circle, but I'm going to use the solid. I'm going to use 3, 3, and 4, 4. To get from 3, 3 to 4, 4, I have to go up a positive 1 and over to the right a positive 1, which gives me a slope of 1 over 1, or 1. Now my equation y equal to mx plus b is y equal to x plus b, because my m was 1. I have to figure out what my b is. If I were to extend this line towards the left, it would pass through 0, 0, which tells me my b value, my y-intercept, is 0. But let's say that you didn't realize that. Well, all you have to do is simply find a point on this graph. A nice point would be 3, 3. Plug that in for your x and y and solve for b. We would have 3 equal to 3 plus b, which means b is equal to 0. Now my equation is y equal to 1 plus x is x plus 0. So it's just y equal to x. And we can go ahead and double check that. We make a table of values. And we start with an x value of 2. It will correspond to a y value of 2. If we look at 3, corresponds to 3. 4 corresponds to 4. So that is y equal to x. Now I have my 3 equations and I have my inequalities. All I have to do is write out my function. This will be f of x equal to, the first piece was x squared. The next piece was 3, and the last piece was x. At x squared, going back to our intervals, it was x less than or equal to 1. So if x is less than or equal to 1, we look at our line y equal to 3, that corresponds to x is greater than 1 and less than or equal to 2. So 3 if x is greater than 1 and less than or equal to 2. And then for x, it was x greater than 2. All right, we defined our piecewise function. Of course, we did it in pieces, but we also have to find the domain and the range. And the domain are the x values. I can just look at my intervals or I can look at my graph. And if I look at the intervals or the graph, I see that I get all the x values from negative infinity to positive infinity. So finding my domain, not an issue. For some reason, I cannot write. I'm in an awkward position. And then my range, that would be my y values. I can go ahead and look at the graph for that. And you see the first y value is 0 at the point 0, 0. And it's solid, so I include it. And then I get all the y values to positive infinity. Okay, so the focus of this section was to be able to graph a piecewise function, and then given a function, a graph, can you find the function? And that is it.